Sve mi je drago mi je, kolegi imaju malo sad problema sa streamom, u svakom slučaju mi ćemo predavanje snimiti pa ćemo to staviti na YouTube, znači mi to stavimo na promociju znanosti, se zove YouTube kanal, i mi imamo internacionalne studente pa oni to snimaju. A zato dosta ljudi, kako se snima, imaju nekakvu tendenciju ne doći. Jer kao u stilu, pa šta ću ja dolazit, snima se, pa će pregledati. Po meni to onako, sad u retrospekciji možda nije baš bila najbolja odluka, ali moramo biti transparentni. Evo, možemo da li pomožemo, ali ja radiš gore.
Okay. Hello everyone. I'm Zdravko Radović, and I'm very truly excited and happy to be here and to present some interesting use case related to most fascinating and rapidly evolving field of AI, is generative AI. I work as a data scientist in Fortinova Group Data Lab in assortment use case, assortment optimization use case. Few words about Data Lab. So at the beginning of 2022, Fortinova Group, one of the largest companies in the region, with over 3.5 billion euros in revenue, operating in 5 markets with over 45,000 of employees in 40 companies, created one cross-company central excellence called Data Lab. The Data Lab uses cutting-edge technology of AI and machine learning to solve some real business problems and optimize daily operations in these companies. So our Data Lab team works with experts from operating companies with over 30 terabytes of data, and current focus is on topics like assortment, pricing, optimization, and promotion. So we have an aspiration to cover all possible topics using ML models in order to satisfy our customers and improve our daily operations. Last year, at the Google Next conference, we received 2 awards, one in Google Cloud Retail Customer category for assortment optimization, and another one in talent transformation category for our efforts in promoting and developing our team. Today I will talk about generative AI and how we solve some problems or challenges using these models in assortment optimization. We used Google Cloud, Google Tools to generate new data, completely new data structures, and I will show you some data structures that we use for another application, and also we will see the common issues that we have that we face while working on this task. We use, as I mentioned, Google tools, Google Cloud tools, primarily Vertex AI, which is central point for all machine learning models. So we use Vertex AI to develop, train, and deploy machine learning models. And also for this specific task, we use some generative AI models called Palm. Maybe I could just switch to see better. So Palm is the first model that Google developed on Pathways infrastructure. So actually Pathways is cutting-edge technology orchestration layer that use massive amount of accelerators, which are actually GPUs or TPUs to train in parallel these large models. So Palm is trained, it's a very huge model. It has 540 billion parameters, and after that, they developed next generation of the model, which is heavily trained on different languages, over 100 languages. And also, underlying models cover different sizes and different fine-tuned models. The largest one is Unicorn, and then you have Bison, Text Bison, and Gecko. Gecko is the smallest model used for creating text embeddings. And the latest model, which is Gemini, it is released recently. It is first multimodal model, which generates and uses different type of data. Now I want to jump into assortment. So, in simple terms, assortment represents some mix or group or variety of different products. And assortment optimization involves serious decisions made by category managers in order to create the best possible combination of items to satisfy customer needs and also to satisfy business needs. So our goal in Data Lab is to help them with using these models to make quicker and smarter data-driven decisions. We built several features, and I will mention only three, which is very important for this task. Our task was to calculate item similarity based on attributes. So item attributes and similarities are important input data structures for these three features. CDP, or customer decision tree, use item attributes to understand and predict customer decisions when they want to purchase item. The unit of needs, or this second U1, is used similarities to calculate similar group of items that satisfy customer need. And third, most important, is cannibalization. Actually, cannibalization uses similarities to predict how change in assortment affect sales of similar products. So our task was to use text as input to generate attributes and also to generate similarity based on attributes. So you can see these are attribute types. We don't have them. Product, flavor, package, texture. Also for the second product, same, but we don't have these attributes to calculate these similarities. And how we did it? We used first model, which was Palm 2, first model that was developed, but it has some limitations. So we provided item descriptions, and for that reason we used text from our taxonomy plus text from Consum Click, which is our e-commerce store, which has better item description. And then we provide this model, and model generates some output. What we saw is that this model is very powerful because when we provide some sparse text, we receive very good quality attribute values, especially like this crispy, which is not specified in the text. But this model has some limitations. First limitation is that it is limited up to 1,000 tokens. So we need to find a way to optimize the prompt and output in order to get as much as possible these attributes. The second thing, which was very which was a limitation, is speed. We actually spent approximately 10 seconds per item to generate this output, which is not good, especially when it comes to the automatization of this whole process. Then we started thinking how to speed up this model. We have option to fine-tune the model, which is very simple using these Google technologies, and that means that we can find 100 or 1,000 good examples to provide the model, and then fine-tune that model with specific parameters, and then use that pre-trained model and fine-tuned model for generating these inputs. So we decided to not go in that direction because in the meantime we received a new upgrade of this Algotrade model, which was text this 152K, and the major improvement was token limit. So we had a wider text input, and also that means that we can now optimize from the scratch our prompt, considering these limitations that are removed. Also, which is very improved, is reasoning, and it was better quality output of this model. So now we have to specify a new prompt, and how we did it. So we actually specified the task in a very clear way. We actually tasked this model. We said you are a retail expert, tasked generating comprehensive attributes for provided retail items. Then we asked model to provide output in JSON format for easy manipulation later. And we provided clear attributes types that we want to extract. And this part here changed from the category to category, because you have non-food categories and you have food categories, so these like flavor is not compatible for non-food categories. And also we stated that the model is allowed to guess attributes which are not stated in the text. We also provided examples to these models, and we saw that when we provided more and more examples, we received better and better output. So in general, we provided approximately 20 to 30 different examples, and we followed the rule that for each category we will see how many group of items we have, different group of items, and we choose one or two examples to provide the model in case to provide better diversity between products. Also, the next thing which was very important is, you probably know, parameters for each model. We use temperature, top K, top P, and also max top K and output, stop sequence character. This temperature is very important in this task, because when you lower the temperature, you will get the highest probability token output. And also the same for top T, top P. But if you want to create some more creative, if you want more randomness in the output, you will increase the temperature value. Max stop in output and stop sequence character you will see later, especially this last one. It helps us to resolve some type of hallucinations. So what are the hallucinations we get? We can categorize in 3 categories of these hallucinations. The first one was very funny, it was made-up products. So we provide item with some input text, it actually ignores it and generates completely fake item. Not only fake name, it provides some fake ingredients, fake nutritional value, and also it assigns correct and true values for these fake items. So we saw that we need to put more examples to avoid that. The second and third one were some unstable text output. For example, this item was true, but along output it generates some unrecognizable text characters, and also it generates some GitHub repository. It exists, but this repository does not have any connection with us. So probably we think that it was some kind of data leakage from the original model. And also the third one was it generates output along with input of the sequence. So we used some special character pipe to fix after this current bracket here and later there. So model generates output, which is correct, and then stop generating another text. So clear setup was these steps. We specified clear context and expected attribute types. We lowered the temperature and the top P values. We add a lot of examples, as I said, and we add these top sequence characters. Also, what we saw after we finished our processing of the items, we saw that we have some correct results, but also they are not consistent, and which creates some challenges when we calculate similarities. So we use simple NLTK library, this stemmer, to find roots of these attributes, and then we post-process them. So in general, what we get is that we are very satisfied using this model. For example, we provided very scarce text, so few information, and when we test this model, we said, okay, let's test it to see what will generate from this text. Maybe some information here will be interesting to other departments, like marketing department. And we saw that it's very good in creating these attributes. Here we have only one more type, which is a unique selling proposition. It's very useful for generating for marketing department when they write copyright for an item. It's actually completely automatized using this model. Also, one interesting thing is that you can create some nutritional and health values, which are also useful for recommendation, for marketing department. So we saw that this model is very, very capable of doing things. I want to jump into these two items from the beginning. As you can see now, we have simple attributes for each attribute value for each attribute type, and now we can calculate similarity between these two problems. So we use a lot of different techniques for calculating, and we finished with some custom-made similarities, which is simple term. We saw how many similar common attributes are shared these two products, and we had some weights which represents what attribute type is more important from customers, and we calculated similarities, which improved a lot these three features that we built. And this is a whole process. Sorry for this size. So we started with this simple model, first version of Palm 2 model, TextVision. We saw that it's very limited, very slow. Then we moved to another one, largest and bigger, and we extended, that helped us to extend input prompt, input text, context. We saw that there is some hallucination, and we added more context. We played with temperature lowering and these other parameters, and when we finished with processing all items, we post-process them and use for item calculation item similarities. As a result, we get over 300,000 attribute values generated, and we save them into the database, and for over 40,000 items. So to conclude, how to reduce hallucination in our case, and we saw from the other colleagues from other industries, they face similar problems when it comes to hallucination. The best usage is when you extract input, when you extract text from a larger corpus. The best is to provide large context, lower the temperature, and provide a lot of examples. Also, you need to find some way to post-process them to capture some unwanted result, because even if you have good prompt, good prompt design, you need to figure out how to catch unwanted result. And that's pretty much it. One more thing before we move to the questions. We want to give you 100 credits to Google Cloud Skill Boost, so you can sharpen your skills and learn these tools that Google offers. So please scan this QR code. It will expire after some time, and you will follow the rules on the link. And thank you. So, any questions?
Did you experiment with some other formats for output other than JSON?
No. No, we didn't need to, because JSON is very useful to store data directly into database. Just iterate of the JSON file, it's very easy to.
But you haven't had like a lot of problems like of LLM generating like not well formatted JSON? So
no, we didn't have that. That's the good thing of this model. We didn't have that problem. So we actually had this hallucination when model generates correct JSON output, but it continues to generate unwanted results. So we use that stop sequence character, and we limited for this output. Okay. Anyone else?
Do you use collaborative filtering? Or have you ever used something?
Yeah, we use a lot. Some features use this collaborative filtering, but in our use case, there's a lot of features. So collaborative filtering is just a small puzzle. So there's a lot of ETL procedures before these collaborative filtering models.
Is the only reason why we don't use like OpenAI API for this, and rather than the Google one, because like you're a partner with Google, or there's
we are partner of the Google, and we received among the first this general preview of the model. So we wanted to test it. That's why we use this form, and we are satisfied because we generated. This is batch prediction. You generate it once and store your data, and now we have a pipeline to generate for the new items when they refresh in the sorting. So it's very useful for this usage. We are very satisfied. Also, the smallest one model, which is called Geeko, it is used for creating text embeddings, vector embeddings. So it is very useful and also very easy to use. They have built a very good API. So you can use them for other LLM features like RAG, retrieval augmented generation. So if you want to build some internal knowledge, or some other, let's say, internal chat with your customers, you can use this model for generating these vectors.
Yeah, and one more question.
Yes.
How do you tackle like if the model like makes some wrong prediction, like it makes some wrong attributes, just that the data which you store, like it goes only for the seeing how similar they are, so they will be like less similar like later in, or
Yes.
or like checking every data point, like, which is almost impossible.
We use this part of post-processing, as you saw. So we sample it. For example, smaller groups, we actually check the values manually, because in the end we put a lot of effort to create good quality of data, because it's one-time job. And also we use them for the examples. So when we provide more and more diverse examples, we saw that we are generating very good quality of data. And then there's small, very, very small, out of 40,000 items, very small, maybe tens of items, they are wrong. But of course, there's no 100% correct model. You always have some error, but we are satisfied with these results.
Did you consider using some multimodal model that can take a picture and possibly give you better or results?
Good question, yes. We have considered that it is Gemini model. It has actually picture-to-text model, so you can, we want to test, but for us, we finished in some percentage our job to generating items, but some other information that wasn't available in the text, we can use this model for generating outputs. But the key thing that I forgot to mention here is the main ingredient and key thing is to have good quality of data, which means if you want to use this Gemini model, that means that you need to have good quality of picture with relevant information. So there can be, you can pay off that usage of the model.
I presume that you gather all of your data through multiples.
Yeah, most of the data, especially this customer data, we use to calculate some similarities based on transactions. So you can see in the data which items are substitutes or complements, so which items are brought together. But also we use the data from the Consum Click, as I mentioned before, Consum Click online store, because colleagues, they manually created very good item descriptions, so it was very good for as input data for a model. They actually typed the nutritional value, some other things, and the model recognized that and generated very good health information, health attributes. For example, you have some items that are gluten-free, vegan, etc., and that is provided from these descriptions of the items. If there's no any more questions, thank you so much.
Thank you. Ja vam se moram zahvaliti, ovo je barem što mi možemo dati. Hvala. Tako. Lara, zvone. Da možda kolege to dođu. Dosta zanimljivo zapravo, zanimljivo je tipa ovi atributi, što ne bi možda bilo jednostavnije tipa, ako se neki atributi sa te kartice pronalaze i svih ostali, da se možda program lijepo sredi, da za svaki model čisto plus ekstrakcija. Zanimljivo je to možda moguće da recimo, kada se populati nekakve kartice ili da prije da su već atributi srednji, da je to slične proizvode i što da se više onako da praviti neki onda oni za koga trebaju naučiti
šta naučiti? Jer imaš proizvod koji slušati, pa ne smiješ biti jedinice, imaš proizvod. Recimo imaš čak to je jedinice, ako ti može manipulovati da neki izvještaj tako da jako puno dimenzija. Jedan od razloga je kompleksna smisla imamo use case, kako god ono mora biti važno situacije, pa i ostalo dakle, to imamo posebno use case, imamo organizaciju informacije, trebaš šta smo dali na katalogu, dobro što smo dali, koliko se toga su mogli bolje, sve moraš da
tu koristite neke modele ovako API izvanja, ali imate možda baš sve internet.
znaš kako mi to razvijamo? Pa se kao što mi sad radimo sa Sifiju, da li još i konsultaciju sa kako živično sopraciju, ako nam ok, moja i onda sa Sifiju, da se da, operaciji, koristiš kako se ponaša, ako se neka stresara, ulazno podatak u kombinire, da će imamo tako pricing,
Mi samo imate sreće, imate puno podataka.
Da.
To je zapravo najveća sreća. Ne znam, to su terabajte podataka. 300 emisija. Ali to ne.
Tekst
svaki
Stvarno, 30 terabajte videa, puno manje nego 30 terabajte teksta.
Sa vanjskima je 20-ak, sa njih ste našli trenutno 12, a s vanjskima 20-ak. Nemamo trenutno svojih resursa pa još.
Ali radite isključivo znači, za ove firme koje su sastav porte nove grupe ili za neke vanjske nalaze?
Sad nam je isključivo interes naše odzvanije i sad nemamo se zvano širi. I diskutabilno je trenutno smo fokusirani samo na retail. Vrlo je upitno da li će neko koja je naša konkurencija, htjeti koja nije podatke s nama, neki osjetljivi podaci su potrebni za kvalitetne rezultate, tako da teško da ćemo u konkurentskim vodama moći kad to je išao prodavati.
Ja baš studiram data science atmosferu, pa sam gledao i firme, ove potencijalno neke, ali vi recimo ste jedina pod broj imate najviše podataka, koje su super za vas, pod broj 2 imate najviše zaposlenih data science za jednog ministra, znači vi imate sad uvijek timove od jednog broja ljudi koji se bave konkretno jako specifičnim use case-ima. A ovo tu je zapravo najviše. Baš sjećam se, kad ste spominjali povezivanje sličnosti item to item, ja sam prije par dana baš radio jedan labos na analizi velikih skupa podataka koji smo radili item to item telemetry filter. I onda sam se sjetio čini ono koji su tu koristili nekako posebnicu, sličnost i tako dalje, jer ista stvar je, te stvari dosta mogu, to je jako monetizirajući algoritma tako da.
Imaš razne mjesta, imaš instancije koje koristiš, kako bi bilo imaš boski, imaš kamera, imaš a imaš i ove custom-made koje mi uzimamo malo dublje i onda vidimo šta je najbolje. Nije samo, ne može svaki model da ti da dobro znači uvijek imaš jedan procenat koji ti ne odgovara i da prši drugu varijantu koji suštini se radi o nekoj orkestraciji različitih.
Da.
Da, vi ste biti uzeli ono, kako ste AI, atribut, samo
rekao, ja do sad nisam ovako išta koristio, baš vezano, recimo, zadnji put kad sam koristio baš konkretno nešto za AI, koristio sam od OpenAI API, ali čisto da mi na moje upite generira tekst i onda bi mi vraćao nazad i da bi ja radio nešto na frontu s tim. To je zato, da nikad nisam ovako baš radio da fino može se atributi ekstrakirati, jer inače ne znam, koji neuronski ti to odradi zabadavaju, to ručno se može, tako dalje.
Tako da znamo da kolegi iz industrije recimo legal tvrtke kreiraju interno recimo možda database i rade retrivanje tih čankova teksta, interni znati koje autorskog ovoga velikog modela. Onda jako puno imaju i tu problema u smislu da im dalje model generiše loša, da taj člank u suštini ti programiš ko operira i taj člank ako nije adekvatno pripremljen,
Ja sam pitao za format, kad ste bili snimali da on lijepi, kad sam htjela čekati nešto dati sam tekst i ugovor ne prepoznaje imena i sad mi je lista imena, ja ništa. Uvijek se napisao sa našim. Čist tekst. Radi tekst. I hoće ona iz članka, tu se članka za tekst. Samo onako kada je osnovna škola tekst. Nešto da se zna koja je osnovna škola. Da sam uvijek imena osnovna škola, ulica, ono. Piše i koji se mi znamo. Uvijek je
tako nešto, kako naš je 700, dobro ti je da prebačiš sve znači da čankaš i da stavljaš, znači dobiješ generišeš da naći koji se naredni pronaći semantički, zato koristiš koji su oni uzeli obzir i semantički samo keywords. Znači, pogledaj semantički je taj riječ na ovom mjestu, šta je značenje, šta je kontekst, razumiješ, zato su koristi i onda ako se radiš sa taj koji se također i onda daš najsličnije semantički taj čan, jer taj čan predstavuješ operinu zakon, jer onda ne zna.
Kada pričamo o realu, ali moja ideja je bila, znači Algotrade tam neki ugovor, koji je najbolji sad, znači neki ugovor, je dosta dana, ne znam, pravo koji je, sad da, baš ne, znači, privatni zemlje bi bilo ono, što ono na sve, a to je rečenica samo izbaciti, poznaje osobno, zamijenili osobno ime, ono, dolar jedan, popiši, dolar jedan, kasnije se znam, ne znam, sam formatik je najbolji, da ne budemo nadalje, i ovdje ne pričam da znam,
U svakom slučaju, hvala vam što ste došli, evo. Tako da, ne znam, petak da smo otvoreni, mislim da smo bili poslali čisto to znate, znači ovo petak.
Znam šta, dogovaramo se tamo da bi u nedjelju trebali za svi nekoga još riješiti.
Tako je.
Dogovaramo intervju.
Okej. U svakom slučaju, mi smo imali ono akreditaciju na čekaju, spremni ste, žiri i sve to, u petak je znači u 5:15 svećna otvorenja, a u nedjelju u 10:15 prezentacija rješenja. Tako da je...
Ja bih iskreno volio, ali nisam tu.
Zrak nam je istali gore, ali dogovaramo se sad interno. Hoće Dragan će vjerojatno doći u nedjelju, ali će nekako s njim još ostati.
Super, okej.
Je li bilo prijavljeno za sve?
Nije, imamo jako puno iz Srbije, užasno puno, imamo puno Bugara, Rumunji, Nizozemska nešto, jedan tim iz Indije se prijavio i jako velika konkurencija dosta. Imamo iz Mostara ekipu, kog još? To sam rekao, veliki koncept. Ne, ovo nam je uzelo sa zadnjih oko 6 mjeseci pripreme za skupa. Ali nije nijedna na ovoj razini. Tako da slovo se možete na LinkedInu sad pohvaliti.
Da, hoćemo. Sad već sam objavila na imamo mi interno svoju na razini portalova grupe, imamo to smo sad već objavili.
Je, može, nema problema.
Svi još novi, svi još
Naravno, mislim, svi su use case-evi, odnosno svi su opipljivi i to je uglavnom ljudima, imamo demand forecast i doslovno tu se prediktaju biti prodaja.
To je super.
I tu smo trenutno fokusirani na voće, povrće i meso i znači, to je nešto što tamo store manager, pa da, jer je najosjetljivije, tako da je važno predvidjeti, ali store manager svako jutro ide na naše rezultate, na temelju toga naručuje dobavljača i fakat je rezultat bitni. U Konzum nema voća i rekao, kaj se desi? Ma mislim, oni imaju mogućnost revidirati naše predikcije, zato što postoje nekakvi vanjski faktori na koje mi i model u teoriji ne zna i onda oni imaju mogućnost to revidirati i to naprave. I bilo nam je biti dosta izazovno kad su krenule sad i neradne nedjelje prošle godine, a model nije to u biti...
Nije treniran.
U biti je, pogotovo se desilo stvarno relativno loše predikcije kad se ispostavilo da je tipa i subota neki neradan dan, blagdan, bilo šta i neradna nedjelja i onda 2 neradna dana. Petak je bila ludnica u dućanima i u biti nitko nije predvidjeti, niti su kategori menadžeri, odnosno ljudi koji naručuju nisu mogli predvidjeti što će se dogoditi, niti su nije model predvidio, to je bilo kaos. Ali treba će sad isto vrijeme za to. Tako da store manager ima mogućnost naše inpute u biti doraditi i po tome onda finalizirati narudžbu prema dobavljaču. Ali mislim, mi cijelo vrijeme pratimo u biti nekakve rezultate i gdje su nam pogreške, tako da znamo u biti da je model načinimo predikta dobro i onda na taj način, mislim, niko ne upire prste u nikoga, samo se kontinuirano nakon prate rezultate. Da, srećem tu nisu tako posljedice, tako da nema otkaza ni ničega, ljudi rade i to je to. Mislim, to je napravno politika, ne to 100% točno. Da, tako to se prati i radi se na to da bude još bolje.
Eto, hvala vam na svemu i vidimo se onda stvarno u petak.
Da, vidimo se.
vidim da imam. Kako napreduje Hackathon? Molim? Ne, možda su ga ovi prednjeli što se zove.
Zvonimir, možda su nam odnijeli ovo.
Što?
Možda su nam odnijeli ovo.
A dobro. Bilo je 7 eura.
Dobro.
Uzeti diodu iz toga i staviti u nešto. Nećemo imati.
Dobro, mogu ja... Ja ću jedan pogledati tako. ali nalazi šasim ga već takvim stvarima.
Aha, jel... Lara, je li ugašen možda ovaj tu? Ugašen je, okej.
Okej, super.
Uvijek je, kako bi rekao, najjednostavnije rješenje najčešće bude, evo ga, to je to sve.
Okay. Može. Na engleskom ili hrvatskom? Na engleskom.
Na engleskom jer zbog internacionalnih studenta snimamo
Hi everyone, I'm Daniel Strasaboško and I'm going to talk about, today about KD trees. I know that the initial topic was arc trees. I'm going to briefly mention something about them. But yeah, most of the presentation is actually about KD trees. I don't have a pointer, so I'm going to sit down and use the mouse. You're going to see why in just a second. Let's start with some agenda. So, first of all, why are we going to look at the KD trees? What kind of problems do we need for them? Then we are going to see the construction workflow. This is basically binary tree. We are going to see details. Then we are going to do the nearest neighbor walkthrough. By walkthrough, I mean literally going through it. Then the nearest neighborhood sketch, because there is actually a hint on how exactly you can implement it yourself, which is I think the whole point. And range search, which is basically, we are going to look at the 2D example, and the range is going to be a rectangle, right? Okay. So, what's the motivation? First of all, what is KD tree? This is a multidimensional data structure which allows space partitioning. K stands for K dimensions, right? So if you have a 2D tree, usually it's called 2D tree, but somehow the practice in the industry is to call it KD 2D tree for some reason. Well, and now, what kind of problem do you need for them? The one really good approach where most of the people use it is in ray tracing. So you have a scene with a bunch of objects, and you put them in a box, and then you want to see the intersection of what exactly needs to be illuminated or whatever, where basically which objects are getting hit by a ray. And the idea is this: if it doesn't hit the box, it definitely won't hit the object inside the box. That's it. And next topic is machine learning, when you want to find the nearest neighborhood of points, and of course the geospatial data, the astronomy. For example, you have some celestial objects or a group of them. You want to find, I don't know, what is the closest star with approximately similar spectrum, something like that. Over here we can see one example from the guy that implemented some rendering part. He's mentioning that if you have a ray which is hitting a ray of light which is hitting a droplet, and that droplet is dispersing the light into a neighborhood points, then you want to illuminate them differently, right? So you need to find out which points are closest to the one that actually dispersed the light, right? And this is then you can see it over here and over here. So that's a nice place where you can use them. Now, I was trying to find some example in the industry, well, not in the industry, in the nature. And there is something which really caught my eye. This is the stalling video. Forgot the name of the bird in our language. I just turned off the laser so you can see what exactly is going on. So this is a flock of birds. This is actually in nature. You can see them moving about, and the guess of the experts is that they are actually trying to create a look in the sky which is going to frighten the predator, right? So they are having some I don't know, high behavior. At one point it even becomes a bird, but not in this video. There is a different one on YouTube. And So what do you need for this if you want to implement it? Yeah, it gets really scary. So even if I was being under this box of birds, I would be, you know, not really neutral. Okay, so one idea is to let's make a small program after this, and they are usually called boioids, so artificial eye program which simulates some flock behavior, and it works on a very simple set of rules which all require that you find out what are my closest neighbors, and this is actually a real great problem to use for the KD tree. Nice, right? Okay. Let's go to the next one. Okay, so let's start with this. Let's pick some points in 2D space, but the idea is that you can actually extend this into any number of dimensions, and you don't lose anything on the reduction of dimension in this case. Okay, so you can see them. You can see them here, and the question is now, okay, how do I construct a KD tree from it? So let's start. First of all, the idea of KD tree is you insert one point and now what? And also which point, right? And what I've done here, I picked the, let's first briefly look at the points. So I picked the A point here, but if you look at the coordinates, they are not sorted by any axis. So what you can do is sort them by X and then pick the median of them if you want to have really good search, but if you don't want to, which is aiming towards the balanced B tree, but if you don't want to have it balanced, then you just pick any point and you basically during the insertion you have to do some additional checks. Yeah. Okay, so I pick the A, which is not the median, and you can notice one thing. It basically splits the space into two regions, left and right. And you can see here I have left and right. Okay, now we have additional point, which is B. Now what do we do with it? Where do I put it? Left, right, what's the deal here? And there is this idea in KD tree, which is you first, when you look at the first, what do we call it? First level of the tree, you pick the first dimension. So the first dimension is X. Then on the second level, you pick the second dimension, which is the Y, and you alternate between them. And if you have multiple dimensions, for example, X, Y, Z, or X1, X2, X3 in the literature, then you alternate between them, and when you're done, you cycle back to and go from the beginning. So the idea is we now compare with the x-axis, and bx, which is in this case is 4, we compare it with ax, which is 2. So it's larger, then it goes to the right. Okay, it's here. Nice. And this, what exactly does this mean for us? It means that the B point is then splitting the right region of the A region, right? Yeah, and it looks like this. Okay, now let's go to the C. So the CX is 4, this is larger than 3, and as I said, on the second level, we are comparing the Y coordinate. This is then 5 versus 2, 5 is larger, then it's going to the right, which means it's going to the top. Okay. And so on. For the D, X3 is larger, for the B is larger, for the C, we are comparing with the X, so 4 versus 3, the C coordinate is larger, CX coordinate is larger, so it means it's going to the left. Sorry, it's, yeah, here. Okay, so it's splitting this region of space into two halves. Okay, and you have the description here. I'm hoping you will get the slides because yeah, a lot of time was invested into this. Okay, now the E point. As you can see, EX is equal to 1 and it's smaller than AX, which means it's going to the left, right? So it's splitting the region on the left. Okay, and we have an F which is 4. Now, one interesting thing happens here. So it's going to the right and it's hitting the C node point. And you need to compare, okay, CX is 4, FX is 4, so they are equal. So where do I put it? Do I put it the top or the bottom, left, right? What is going on here? And the idea is this. You will see it on the web in many examples. It depends on you. It depends on the implementer. So it can be, and I'm actually using in, I have two examples here. One is this one, and the other one is using the reverse. So in this case, I'm going to say, okay, I'm going to put it right, as you can see here. So it's splitting the right side of the C space in half, right? So I put it basically here, and it's splitting this space into two halves. But also I could have picked the other space here, and it would go there, which would then compare with the D. And you need to know about this because it's only comparing what is the value of current point and where do I put it, and you need to decide for yourself. Am I going to put it left or am I going to put it right? And once this is basically in the algorithm, you have a value of the current point. Is it larger or is it larger and equal to the value of the point I want to insert in the graph? That's it. You just need to know about it when you construct the graph and when you want to use it for querying, because it depends where are you going to search. Am I going to search for the same value in this node or in some other node, which is probably just on the right. Okay. So basically this is it. We have constructed the 2D KD tree. This is for the endpoints, and as you can see here, I'm not going to prove it, and I don't know how to do it. This is n log n, basically, which is much faster. Well, it's not much faster, it's only faster than what you can do with something else. Or in storage, because yeah, you have endpoints. One important thing to note here, you will see also in the other example, that examples on the web tend to have the points as leaves at the bottom of the tree. So what's the difference? The difference is how actually do you want to use the tree, and what are you creating? What's the most flexible thing for you? If you want to know at the first possible time some value inside the tree, then if you don't want to go to the nodes, you know, the leaf node, you can just save the data on some specific node in the tree. But you know, you can go either way. It's really, it depends on you. Okay, let's now go to searching. We are going to look at the 3 classes of search. There is actually a 4th one, but I actually don't have time to show it. It's basically a radius. So you pick a circle around your point and you are inspecting all the time here, is it inside the circle or the sphere or some other geometrical body, or is it not, right? You basically try to find out which points are inside it. But with the range search, you are actually going to see how to do it. Okay, let's start. This is it. This is our starting point, and someone gave us this point here called T, and the question is which point from our space is closest to it, right? And we can visually see it's actually E, right? It's no problem. But what if you have millions and millions of points? For example, you saw the flock of birds in 3D space. So if you pick a bird, which bird is closest to it? You don't know. You don't know even where to start. And with our KD tree, you can find out that info pretty fast. It actually takes just a couple of queries down the tree to get to the exact closest neighbor, right? Okay, so let's start. First of all, we start from the root and we calculate the Euclidean distance, so this is the shortest possible distance, from A to T. And this is 4.5. Okay, now the question is, what now? What do I do? And the idea is, okay, we know that A point is actually splitting the space in two halves. Which one is from these two halves closer to the T point? And it's this one on the left. So if we need to now go to the left, right? Okay, blah blah blah. Yeah, this one. And we enter that region, and because I saved the points here, I can immediately calculate that the distance between T and A is 2.2. Okay, and this is now current best value that we have, the shortest possible distance we have currently found. Okay, and now the idea is, if you have this node, it probably has some children, and you want to know, and this is a really important step, you want to know which way I go first. The same thing as we did for A. Where do I go now? And the idea is always go to the probably the best place that is closest to T. And in this case, this is the region above the T, right? So the up. And you are checking, hey, do we have any points there, or the subtree? And we don't. So you mark it as checked. And now you want to know, and what about the other half of the space? Can I have any point in here which can be closer than the currently 2.2? And the answer is yes, I can have a point just here, which is thing 2, yeah? And if I had a point here, it would be closer than what we currently have, the point E. But we don't have any points there, so it's okay. We mark it as checked, and we now go to our root, which is the A, and we want to know, okay, and what do I do now? Do I need to check the A, the right side of the space that A is splitting? Let's see. So, can I have the closest point here, which is better than what I currently have with E? And the answer is, again, yes. So this means I actually have to go to the right side of the tree. And when I go there, the next point is B, which is actually pretty far, right? It's all the way here. So that's not better. Now the question is, okay, what do I do now? What do I do now? Do I go up or do I go down? Because the B is splitting with the, you can see it here, down and up. And of course, what we want to go is up because it's closer to the T point. Here. Okay, and when you go there, sorry, when we go there, the next point is C. And when we calculate the shortest distance, we can see that it's 4.5, right? So definitely not better. But we are still not in the region of the so-called the critical space, you know, the one over here. Okay, and we are now in it. This is then the D node. So we were at the C point, and now we are again making the decision: do I go to the right, which is further away from the T point, or do I go to the left, which is more closer to the T point? And we go to the left. Okay, so we are there, and this is the point D. So D point is not better. It's 5, distance between T and D. So what do we do now? We are still not in the region which could actually have maybe the closest point, because that region is at the top of D. It's this one here. And if we go there, we actually see that there is nothing. So, okay. Now the question is, and what about this half here? Do I need to go there? And if we actually take this rectangle and measure the shortest distance between the rectangle and the point T, we can see that it's actually worse than what we currently have as best, right? And we can just say, okay, I don't care about it. The X means that we have pruned the tree. We marked it as I don't care about any point in this region. So we are completely ignoring it. Okay, this is really important because the gist of this structure and the algorithm is that you know that you can ignore a bunch of other things which you can be certain of they don't matter, right? The strength is in ignoring the stuff, not in calculating faster. That's the idea. Okay, now we go back up. This is now the sea level, and we ask ourselves, okay, the right side of the sea, can I have point there which can be closer distance than what we currently have as best? And the answer is no. This is too far. And we mark also this part of the tree as invalid candidate, so to say. And that's it. Now we are left with the B because we were here. This is, we don't care. We go to the top. We are done. We have explored all of our children. We go to the top. We see that the down hasn't been checked. And we are now asking ourselves, okay, and can I have any point here which is closer to the T that is best than what we currently have? And the answer is no. This is too far, and we are done. We are pruning that tree. We can have millions of points here. We don't care. We go to the A level. All of our children have been checked, and we are done. We have found the closest point, which is E. And we have ignored point F and all these subtrees here. Yeah. Okay. And so you have just learned how to do the nearest neighbor search in KD tree. Congratulations. Okay. Now, to basically stretch the algorithm a bit so you can see it more vividly, let's move this point T even further away. So it's really, you can actually see that the closest point is really the E. And when you do that, you can see that all this right side is pruned. So you do check here, you go into here. The E is closest, it doesn't have any children, and you just go back. That's it. This is how we found out this is the closest point. And sometimes this happens, sometimes not in practice, but I'm just trying to show you visually how the pruning is the essence of it all. Okay. Now K nearest neighbors. It's K and N. I don't know who decided to call it K when we have K dimensions. It's a different K. Okay, so what's the idea here? You are using the same algorithm as I just shown you, and this is just a sketch. I'm not going to do a walkthrough. So the idea is this: you need to have a support data structure. So the main data structure is here, and you need to have a small additional one whose size is equal to K. So if you want to find three closest points to the T point, you need to create additional structure with the size of 3. And this data structure is max heap. So you just, when you find the best candidate, you just put it on the heap, and yeah, that's it. When you are done, when you have explored everything, actually not everything, at some point you need to prune the graph. What is the criteria? Yeah, I think the same thing as here. You need to do the same point as here. You still need to do the pruning of all the points like we had over here, right? You would have the same thing. But you would probably continue if you don't, you would need to check in the heap what is my worst distance inside the heap. Yeah, that's right. So you are, so if you have 3 values and the third point is the most distant one from the P, you use that value to compare with the rest of the tree here. Do you need to prune it or not, right? So how do you decide if you want to go here into D or to B or to E? You need to check the worst value in the max heap tree. Okay, that's just a hint. I really recommend trying to implement this. It's fun. Okay, let's now go to the region search. This is pretty interesting because it actually, as you can see, it's a completely different tree. We don't have the same values and names for the points. And the idea is this. Also, yeah, the most important thing is maybe as you can see the points here, I actually as the leaves in the graph, right? They are not some node in the graph, but leaf. And the another thing is, if you have a point on horizontal line, for example, P1, now the question is, to which region does this point 1 belong? Is it below or above? And our decision is to put it below. And if we have, for example, this point P9, which is on the vertical line, we then put it on the left, right? And this means that all the points are in some of the regions. So we don't have the same thing as before where we could have the null for trying to see does this subspace contain any points, and we notice that it doesn't. I mean, what's the point in that? Okay, so this is our starting point, and we want to see which points are inside this rectangle. That's the problem. And we call this query rectangle or search rectangle. You will see it in both terms. Okay, so the starting point. Well, this node here, it has a coordinate x, which we use. And this x is basically determining where we want to go in the tree. Do you need to go to the left or to the right? Because it's not currently clear. And the idea is this: if it cuts the box, the rectangle, then you have to go both ways. That's it. If it didn't cut this region here, if the complete area of the rectangle was on the right side, you wouldn't go to the left. That's it. That's the whole idea in current scope. Okay, so we need to go to the left. Let's do it. And we are here. Now what do we do? This red dot here is actually the line that was drawn to the point 2, the P2. And we can see here that this line doesn't actually cut the y-axis, y-coordinate. It actually doesn't cut the rectangle. That's the gist of it. So it means that we should go to the region which is closer to the rectangle. Okay, and this is the lower part. Okay, we are there. Now we have to cut it. This region is cut into 2 halves, left and right, and we go again to the right because that one is closer to the rectangle. As you can see here, actually I was jumping a bit, and when we are here, in this region, which is here, am I missing a slide or what is going on? And when we are here, the point is that you check in this remaining region, hey, do I have any points there? and it turns out that we do, and this is the point P3. Okay. And now when we found the point, and this is the only region that has the space of the rectangle, we go up, right? We mark the P3 as inside the rectangle. Basically, you need to have the function, hey, is this point in the rectangle? You can do any kind of trickery there, but you need to check. Okay, now we are done. Let's say that we actually mark this P3, and we are now in the right side of the tree. Actually, no, I'm wrong. It's not in P3. Is not in the tree, in the rectangle. What am I talking about? It's been exhausting day. Okay, now we go to the right side, and we want to see. Okay, we are cutting this space in two halves with the y coordinate. One space is above, one is below. Let's first check the space above, and in there we have 2 points, P1 and P2, and if we check both of them, we can see that they are not in the rectangle, and we are done. Okay, now remaining space is the one below, and we have it split in two, and both of them are in the rectangle, right? And what we do now, we check for the, basically we can check for either way, be it this left side or the right side, but I chose to pick the right side because it's prettier for the illustration. So we mark P11 as inside the rectangle. Okay, we are done. As you can see in this is no longer marked as red. And we have now this y coordinate splitting this space into regions. And we now do a check. Okay, P6 is, as I said before, if the point is on the horizontal line, then it's actually below it. Which means P6 is located here, and we do a check. Hey, are you in a rectangle? Yes, I am. Cool. Okay, now what about this space here? And this is crucial, because if you have millions of points and you just pull a rectangle over most of them, you don't want to go into every subsection of the tree and check, hey, are you inside this rectangle? What you want to do is do some trick, basically, which is a conclusion trick. And the idea is this: if you have checked all the regions around this rectangle, then you know that this rectangle and all the subspaces, belong to that rectangle if you have checked the subspaces around it. That's the idea. And we have done it, right? We have checked this space here, we have checked both of these two here, and we have checked this one here. So the conclusion is that everything inside it belongs to the rectangle. And you don't need to now iterate through all the tree, you just need to say, okay, this part of the tree, it's inside it, and that's it. Yeah. And that's basically all you need to know about region search. I know it's been maybe how it's called, digress. But yeah, by the way, we had, I'm going to show that later. So the runtime of this is, you have endpoints, and the idea here is that this K is actually not the number of points, but number of checks for the regions here. This is usually called the output, but it's still the squared time. And this is axis parallel rectangle. Just imagine you just rotate it a bit, which is then completely a different problem, because, yeah, let's not get into it. Yeah, okay, and if you have D dimensions, which is definitely possible, then it's, yeah, as you can see it here, something else, but still okay. We are actually at the end of it, but I wanted to say a couple of things with where exactly do you need KD tree? The idea is this: a large number of points, millions, and a lower number of dimensions. So 2 to 3D dimensions, not, for example, I don't know, 20, and definitely millions of points, not some, I don't know, 1,000. That doesn't make any sense, because linear search would be even faster than creating all of this and wasting the time. Yeah, this is it. Thank you. Okay, any questions?
Yes. Can we go to the picture? If you can check the right down.
Sorry.
Yeah, this picture.
Yeah.
If we didn't go to the P11 before going to the left side of that line, would we have to check all these points?
You said that we didn't go to P11.
If we didn't go,
Okay.
if our algorithm first checks the left side, not the right,
Okay.
would we have to check all these points, and we wouldn't get it to conclude until maybe some of these points would conclude?
Yeah, excellent question. The answer is yes. So you can definitely have. I mean,
is there a way to, let's say, go from outside to the inside of the square to maximize our chances of conclusion?
Yeah, you basically you are saying, okay, how do I actually circle around the?
Yes.
Yeah. I mean, I don't have any code now. I tried to write it, but I just was out of time. The idea is, let me try to think of something, because that's the whole point of it. If you circle around the area, you can circle. What's the word? Encompass the rectangle. I'm not sure, because let's say that this rectangle actually was even. But wait a second. The tree is always cutting the space in such a way that, for example, as you can see here, we didn't first come to the, I don't know, to the P8, because the P8 is over here, right?
Yes.
So we didn't enter here. Why? Because we are actually going from the furthest points and to the inward, right? So the tree is guiding you from the outside in, so to say. If you remember this one here, we were actually further, and we were getting closer and closer, right?
Yes.
We weren't coming from the middle to the, checking the outsides. We were coming from the outside towards inward, outside inward. Yeah. So I guess this is my guess, that the algorithm is working in such a way that it comes from the outside and encompasses the rectangle area, but this is not proven in any way by me. This is just a guess, right? How would I actually make an edge case here? Yeah, that's a good question. Yeah. So my answer is, this is the property of the tree. When you are querying, that you are actually always coming towards the thing you are looking for. Yeah. One important thing to note is this one here. So what I've done here, actually I have even better. This one here. So what people usually do, they come in here and they pull the shortest possible projection on the y-axis and check, hey, is this distance still shorter than what we currently have, which is 2.2, right? And this is their check, which is sometimes correct, sometimes not. So my rule of thumb is always calculate the shortest possible distance between rectangle and the point, because the runtime of the calculation is, I don't do them that often. In my case, I don't do them that often that it matters. It's I care more about the answer, which part of the tree do I need to ignore, right? That's the answer I need. I don't need, hey, is this really the shortest possible distance? And then if it is, I'll do something. The point is, what I definitely can ignore. That's the gist of it. So if you pick a projection which is maybe not correct, you are going to enter inside this tree and start checking it. And if you have a couple of thousand items there, it's going to be larger than the runtime to check the shortest distance between the rectangle and the point. That's my impression. Okay, let me now show you something else which is more interesting. Do you have any questions related to the images, maybe? Okay, something more exciting. Just a second. Do I need? Okay, I have this here. Ooh, this looks hideous. Oh, God. Okay. Mouse is here. So this is the program we work on in AVL. And let me just show you some examples where we use the KD tree, right? So this is a bunch of polygons, a bunch of points here. I'm only showing you the polygons, right? It's nothing else. And these are connections between the polygons, which represent the roads, nothing special. And the idea here is you can actually see everything here, which is only visible in this debug mode. Bless you. And when you go over it, it shows you some coordinates, right? And if you go to someplace else, it shows you different coordinates. And the idea is we have a bunch of polygons here, and if I try to find something larger like this one, right? This one is much bigger, and if I just go with my mouse like crazy, it still manages to find the polygon and calculate me the coordinate inside the coordinate space of that polygon. And the polygon represents something like a road, right? And the road has its curvature, has its geometry, and you have the, basically you can say, hey, how am I positioned with my car in this road? And then you can see it in here. Yeah, you see it's a bit laggy, so our drawing is not that good, but our querying is, yeah. Let's maybe turn this off. Okay, now it's a bit betterish. Okay, yeah, that's one of the ways we actually use the KD tree and the R tree. So when you want to use the R tree, you are basically not saving points and querying points. You are querying what is the polygon underneath this point. That's it. And the idea is that you can have the orientation of the polygon also, like in if you have volumetric structures, boundary, BBV boundary, no BV boundary volume, something like I don't know. The guys who work with ray tracing do know these structures better. Okay, that's it. This is how you would actually use this tree. Yeah, that's it. Okay, I'm going to stop sharing now, and that's it. Thanks.